All right. I think that we can jumpstart here. So I'm very, very happy to have another talk of our series of discussions in science and technology. Today we have with us Erik Larson. He is a computer scientist, tech entrepreneur, and author of an excellent book called The Myth of Artificial Intelligence: Why Computers Can't Think the Way We Do. I had the pleasure of getting to know his book last year, and I read it, and as soon as I finished it, I posted it online because I wanted others to know that the points here are like pretty sharp and important to counterbalance what we see in many places in the news media, for instance, that AI is going to dominate the world, and that we are going to have like this scenario of dominance, things like the ones that Ray Kurzweil normally tell everybody. But today we're going to have the other side of the coin, why we are far from that point and the limitations of AI. This talk today is part of our partnership with the Catholic University in Rio de Janeiro, PUC-Rio, and the Institute of Computing here in Campinas, Brazil. And it's also organized by our lab here, Equated AI, the Artificial Intelligence Lab. So Erik, thank you very much for joining us today and for accepting this invitation. I'm sure that's going to be a very nice discussion. I'm going to spotlight you to everybody. Feel free to start whenever you are ready. Normally, you present, and in the end, we have questions. But if you also allow people to ask along the way, it's up to you. Okay?
Sure. Well, thank you. I typically don't script these very much, so there's always this kind of element of I wonder how this is going to come together. But fortunately, I am talking about a book that I wrote, so it's going to be a little bit hard to get too far off track. Although I've done it, so I hope I don't do it here. But so yeah, I'm Erik Larson. I work for, currently I work as a research scientist at a technology company in Texas. And my sort of specialty is language processing or natural language processing, with basically working with unstructured data and building language models. I have another kind of focus with there was some kind of reverberation there, or there was something. I'm not sure.
I took care of that.
Okay,
so please continue.
Yeah, so that's I have another focus in what we used to call the semantic web, which is now kind of subsumed by the knowledge graph community, where you're working with a markup language like RDF or RDF schema, and of course then there's logical extensions of that like OWL and so on. And so I've worked pretty extensively with that community as well. So the question is, why did I write a book called The Myth of Artificial Intelligence then, right? And so I guess I would say, like, so I'll just, if you can permit me a little bit more of this bio stuff without, I try not to bore everyone to tears, but I think this is, maybe it will become a relevant point later. I've seen I'm old enough that when I started my career in what we now call AI, it was the year 2000. So basically for the entire 21st century, I've been working on these problems. And I've seen, we're right on the cusp of the explosion of the web in the year 2000. And at that time, we were still working with what we now call classical techniques, They've been kind of somewhat pejoratively referred to as good old fashioned AI, but this would be using broadly deductive or rule-based methods, and we just didn't have large enough data sets to make what we used to call empirical methods, or what we call machine learning methods. We just didn't have enough data typically to make those those approaches actually have much utility. So I started working for a company called Sci-Corp, which is it's a kind of famous in the annals anyway of AI, in the history of AI. It's a kind of famous company for the reason that it spectacularly failed over the course of about 30 years to build a giant I sometimes refer to it as a giant brain, but it's basically it's a huge axiomatized, it's a knowledge base full of all the common sense that the engineers can axiomatize or express in a logical language. And the idea was that when we reached a certain number of axioms and rules in this giant knowledge base, or KB, that it would start to exhibit non-brittle and intelligent behavior. And so the Department of Defense and DARPA put quite a bit of money into this, and then it turns out in the end that it wasn't a viable project. But anyway, it's a very historical project. That's what I started working there as we used to call an ontological engineer. And so I've seen kind of both. And then, around 2005, it was fairly apparent that we had so much text and unstructured data on the web that all these old techniques were going to show promise. And so back then, neural networks were actually not very popular. Certainly people knew, backpropagation has been around for quite a while, but it was not a particularly tip of the spear type of tech. But then we were using, different kinds of graphical models. So we'd have the Bayesian set of the graphical models, and then something called support vector machines, where you have these wide margin classifiers and so on, and max entropy, and all these kinds of things, decision trees. And so we had this assembly of different techniques that we used, and basically we were trying to make spam filters and develop very rudimentary conversational AI, and do pretty much what the web has become. Like in the early stages of that, when I was in Austin, we were trying to do all those technologies using those different approaches. So that's kind of that's enough about me. I think that's pretty much what I've been up to. And so I wrote the book. It actually occurred to me around the mid 2010s, around 2005 or so. There was this huge explosion of the kind of singularity stuff that started happening again. And right after the .com bubble burst in 2001, nobody even said the word artificial intelligence. It was considered a buzzword. And so if you wanted to talk about the tech that you were building in computer science, you mentioned the specific algorithm that you were using and the specific approach, because calling something artificial intelligence was considered just real lazy and silly marketing speak in the year 2000, 2001, after the .com bubble burst. But of course, by 2005, we had Web 2.0, we had sites like Dig, there were the beginnings of the social networks, and of course, Google was just a gigantic 2005. So we had this new suite of technologies, and the AI word came back in. And it occurred to me, like, this has nothing to do with science per se. This is just we're just kind of riding this wave where this marketing term comes in and out of our daily discussions as computer scientists, depending on how things are going, And so Kurzweil, of course, Ray Kurzweil is a famous futurist who now is, I think, director of engineering for Google. but he's got this idea that by the end of the 2020s we'll have a general intelligence, what he and others call an AGI. And he wrote a book in 2005, which also prompted me, called The Singularity is Near. And most people understand, if you're working in computer science, you probably have come across the sci-fi set of concepts that involve computation. And the singularity is this idea that we're marching towards this inexorable point where computers are just radically smarter than people. And then we just don't know what's going to happen, because we'll effectively be like, pigeons or some, like birds that, compared to these super beings. And so that the singularity has a lot of different meanings, but the basic idea is that the future just gets away from us because of the intelligence of machines. And there's an implication that the machines are actually conscious, right? Like it's not that there's just a bunch of mindless computation going on controlled by some Russian hackers somewhere. It's that the actual machine is the negative force. The actual machine is the threat itself, because it's become sort of conscious and aware of itself and smart enough to cause us all no end of trouble. So I thought, well, this is interesting. 4 years ago, we couldn't use the word AI, and now the singularity is near. Here we go again, right? And so I thought, okay, I've got to write something. The public should know that as a practicing computer scientist, I personally don't see this inexorable or march towards these super smart machines. In fact, I see a bunch of engineering exercises where smart teams, designers, get together and they decompose a problem with a set of tools. Like these tools would be like Python libraries, for instance, or before that it was Java and so on. And so you basically, I see computer science as an engineering discipline that solves a very large potentially set of problems. And so I wanted to get that view out and make that view clear. And so that's why I wrote the book. Now, if you look at the date of publication, it's 2021. So it was, 15 years before, it took me a while to write the book, obviously. It was not entirely, just as a side note here, it was entirely unclear to me how to write a book that was effective for a generally educated audience, but also that wasn't insulting to someone with a PhD in computer science or what have you, right? So it was just a puzzle it was just endlessly a puzzle to figure out, how do I do this? And so I think that's probably the best segue. So I just completely ignored the consciousness stuff. Like when people start saying that, machines are going to be conscious or they're not going to be conscious, I just figured those are such deep philosophical issues that it's not going to be productive at all to try to shine a light on those. So what do we know when we're building AI systems? What's really where there's a very important concept at play is the idea of inference. And inference is just this, very colloquially or broadly speaking, it's given what I already know and what I can observe, what does it make sense to conclude or to believe? And so you can't have, if you don't have inference, you just don't have any sort of cognitive capability. You don't have a robot or an autonomous navigation system that can navigate, a living room or a busy street. You don't have a Turing, you don't have any kind of conversational AI, because there's endless inferences involved in just understanding a conversation in a natural language. So you basically just don't have what we know of as AI if you don't have some answer to how does it perform inference and what types of inferences does it perform. And so I actually studied mathematics as an undergraduate. And so, and I'm sure many have this is not unfamiliar territory for many people, that, the inductive inference or induction has been developed extensively both in mathematics and also in the broader scientific community it's basically observation-based inference, right? So from a set of prior examples, you can conclude a rule. So the classic inductive inference would be, I've seen so many, n white swans, and therefore I conclude this rule that all swans are white rather. Now that's not certain knowledge, and it can be falsified by one counterexample. So famously, a guy, Taleb, who is a former stock trader, and now I think he's just writes books and so on. But in 2007, he wrote a book called The Black Swan, and when he was talking about stock markets, he was saying, look, if you use induction to make money, in other words, if you're looking at a prior trend, you're doing induction because it's prior example, right? You can see that, right? So and if you're doing that, then just one black swan is going to is going to ruin your day. So like he made a somewhat more complicated exposition of that. But we use inductive inference, and in fact, what big data is and what deep learning is of course inductive inference. It just is the provision of a data set and the features that are already specified in that, syntactically specified in that data set. It just is that provides the inferential power to a deep learning system. So, okay, that's interesting. Then of course, deduction and its variance is, we can just, you could write people have written, by the way, many PhDs about what deduction, but it goes all the way back to Aristotle in a various form. It's a syllogism where you have two premises and a conclusion. Most people are familiar with, they're still, named in Latin. So you have modus potens, if A, then B, A, therefore B, right? And so this logic, these kind of conditional expressions have a formal semantics, which makes them different than just writing. If you're writing in Python and you say, if this is true, you're not saying if this is true, then this follows. You're saying just if whatever, then, whatever, right? Like, so there's no formal semantics backing up conditional expressions per se in a programming language, but in an actual deductive language, that actually is backed up with a proof theory rather, and a model theory. And so deduction broadly is a rule-based way at doing inference, and it doesn't rely on prior example. It relies on the provision of knowledge. And so this is kind of the idea that you have a knowledge base, and that knowledge base is adequate to, to characterize or axiomatize what you want to reason about and infer. And so, so that's a different way of doing AI that's been explored since its inception in the 50s. There's been tons and tons of rule-based systems, some very famous ones. Most chat bots now they're actually, they're more inductive, but a lot of chatbot systems used very complicated rules that tried to capture some facts about language and some facts about practical conversation. And by the way, deduction, AI systems that they used to be called expert systems. They were used in medical diagnosis. They were used in chip design. Actually, you could actually prove whether some chip was adequate given some specification, and that actually would use the deductive AI approach. And so it's a very rich area. Deduction, it's not what we're doing today, but it's the second. And then, so I thought, okay, look, you can divide the entire history of the field of AI, roughly speaking, into deduction and its variance and induction and its variance, right? And then hybrids, hybrids where you have both in play. And so it's okay. Now, is deduction and induction as types of inference, are they adequate to generate general intelligence? And the answer is no. If you look at a true cognitive system like a human being, if you just relied on deduction and induction, you would be the largest bizarre moronic, you would resemble an AI system, right? for all sorts of reasons that I don't necessarily want to get into, but it just is demonstrably not the case that using just deduction and its variants and just induction or any combinations of those that you can actually get general intelligence. It turns out that you need a tripart distinction in inference. You need one more. And it was famously described by an early American mathematician and kind of philosopher, statistician. He was a kind of polymath named Charles Sanders Peirce, and he called it abduction or retroduction, but it usually goes by the name of abduction. And abduction is, in its simplest form, it's actually a logical fallacy. So if you look again at modus ponens, you have if A then B, A therefore B, and you want to see the sort of abductive equivalent of that. You actually use something called affirm the consequent, which is a logical fallacy. So you say, like, if A then B, B therefore maybe A. And it turns out that most of the intelligent inferences that we're doing when we navigate a busy street, make sense of, why is my coat not where I thought it was when I walked in, have a conversation with the neighbor, go shopping. It turns out that most of the inferences that we're performing are actually of this broken deduction kind, or this abduction kind. And the other way to think about this, if you put it into an actual example and out of propositional logic, you can see it a little more clearly. If you say, like, if it's raining, the streets are wet, therefore it must be raining, or maybe it's raining. And it was there's a set of conditions that can account for the fact that the streets are wet, and the rain is one plausible one. But you need all kinds of new information. You need causal information about what's happened before. You need some basic contextual information about what plausibly would make streets wet. Maybe the kids are running around with the super soakers. Maybe there's a fire. Maybe all over the news there's a giant fire and they've got these tankers full of water. They wouldn't be full of water, probably. It'd be full of some kind of retardant fire. But maybe one of those, like, inadvertently or just accidentally dumped a few thousand gallons, and maybe your neighbor drove over the fire hydrant and just right around the corner there's a huge mess because of there's all kinds of reasons that the streets could be wet. And the point is that there's no way to infer that typically without having a causal and contextual connection to that bit of reasoning that you want to do. So we're using a broken kind of deduction called abduction when we're doing anything interesting. And certainly you wouldn't say this is the deep learning way of deciding that it must be the rain that caused the wet streets. I've seen 10,000 examples of the streets being wet, and every time it was rain, and it was never. This is why deep learning and just machine learning in general is so horrific with counterexamples, right? Because the more confidence you get in a model, what you're basically doing is it's an exercise in confirmation bias. You just keep adding positive examples, right? And so eventually it develops a very rich statistical model because it's seen so many examples. So if you're going to just be moving from deduction or abduction to the induction game, you're using a convolutional neural network to figure out why the streets are wet. And it says, like, yeah, but I've observed for the last 10,000 times it's always been rain, therefore it's got to be rain. Well, I mean, it's not hard to see how we don't need that kind of intelligent, quote unquote, intelligent system taking over the world. I mean, that's, forgive my language, but that's pretty stupid, frankly, right? Like, well, I've seen this 10,000 times before. So there's just no ability to see that it's not the case, that it's not the rain this time, right? So I spilled a lot of ink in the book just explaining what inference is, that there is a tripart distinction that we're aware of, that we know a lot about it, formalized and discussed in science and mathematics for literally centuries now, and that we know demonstrably that we have two types available to us that we can program in AI, but unfortunately, neither of those types are adequate to get intelligence. We need this third type. The problem is nobody has a clue how to do that. Nobody has the slightest clue how to make an actual causal, sensitive, abductive reasoning module. word abduction exists in the CS literature. In fact, one of my Ray Mooney in the computer science department at University of Texas at Austin has done a fair amount of work trying to use Bayes nets to do what he calls abduction. But I call this abduction in name only, because if you're using a Bayes net at the end of the day, you're using what? You're using induction. So you're masking, you're trying to sort of create the illusion of abduction by using induction, and that's not going to work. The types are distinct logically, and they're irreducible one to the other. In other words, you have an exhaustive and distinct set. So what that means is that induction simply cannot be made to do the work of abduction. They're just distinct inference types. And so you combine that with the fact that we need all three to generate intelligent behavior, and we've got a big problem in AI. We need some kind of major conceptual advance before we're going to make any real progress on these broader goals. And so it wasn't a surprise to me. I don't want to say, I don't want to sound like some kind of, like I told you so or something. I mean, but it was not a surprise when AlexNet came out in 2012. There was a lot of interest in convolutional neural networks, and then of course when the big tech companies figured out that you can use GPUs to train these huge compute intensive networks, we had some really good performance in visual object recognition, leaped forward. A lot of stuff in NLP got a lot better. Alexa got a lot better, right? Autonomous navigation basically uses a deep learning kind of brain to do fusion, sensor fusion. So we saw a lot of really cool sort of F measure accuracy progress on some core areas in AI, but it was not surprising to me at all that 10 years later, it's 10 years since AlexNet, it wasn't surprising to me at all that we wouldn't have anything approaching general intelligence, because I'm sitting here thinking about this inference framework and I'm thinking, that's induction. It's not, Alexa is not going to understand what you mean ever. It doesn't matter how, if you give it a larger data set, bully for you, it's still induction, and that's not going to be enough. And so, and I'll say the same thing. I mean, like we need, in my view, and what I argued was that we need a conceptual advance that we don't have a clue yet what it is, such as the nature of conceptual innovation, right? Or we should expect that the systems that we have now will look a lot like this. The systems of the future will look a lot like the systems we have now, only they'll probably have a lot more compute power, and they'll be doing, we'll have more killer drones and more surveillance cameras, but we're not going to have true general intelligence until we have this innovation. And that, I mean, that's where I think we're at with the field. Yeah, that's depressing. I want to say it's not what's impossible or not impossible that I'm interested in talking about. I have no clue what's possible or not possible. I'm saying, like, what is the actual challenge that the field faces? What is the real challenge? Let's get to that and not sidestep that or kind of, fail to discuss that. And then let's figure out sort of what we need to do. I think that's all I want to say. I feel like I've been talking just for hours at this point. So I think I just want to stop there and see if, if there's any questions. I hope that was good enough. Yeah.
Yeah, I think that you laid down the argument. I just asked people to type their questions here. Let me put myself also in the highlight mode. Okay. And also my colleague from the Catholic University of Rio, I think that he is here, Marcos. I think that he needs to turn on the camera. Marcos, try to turn on your camera now, please. Add to spotlight. All right, so welcome Marcos as well. Erik Marcos is the director of the Department of Informatics at the Catholic University of Rio de Janeiro, which I told you is like one of the best cities in Brazil to visit. alongside Salvador.
Perfect.
And Marcos, thank you for joining us.
You bet.
All right, so Erik, we will start rolling the ball here. One of the arguments that you make in the book and that you explained here today is that we need three elements, basically three elements for intelligence: inductive, the deductive part, and the abductive part. And we have seen a lot of deductive in the past, like a prologue and large systems based on rules and things like that. Then we've seen a lot of innovations like this in terms of induction with deep learning. And you say that you don't think that we have now anything that's close or in the direction of abduction. This is when you wrote the book like a year ago. From that point to today, have you seen any sign that we are trying to at least explore something in the direction of abduction? Because the argument that you make in the book is pretty much similar to the argument that Judah Pearl also does in his book, that we need causality, we need causal model.
Yeah.
So have you seen anything different from the moment that you inked those words and now?
No, I mean, well, the short answer is no. But I haven't done an exhaustive lit search since the book came out. So, maybe there's something out there, but I have this clever argument for how I'm fairly certain that's not true. If there was a real leap forward in abductive inference, then it would be we would be aware of it, because it would be making significant waves. So the fact that that's not happening, sort of counterfactually, but no, I mean, the Allen Institute in Seattle, Oren Etzioni he's a former University of Washington computer scientist. He's a very good computer scientist, also an entrepreneur, and he's now heading that. And he has a abductive inference project under the purview of the Allen Institute for AI, but it's basically a binary choice between, it's a very contrived and constrained version of abduction. It's abduction in name only. And it's also driven basically by parameterizing and using data. And so it's also basically, at the end of the day, what it really is an inductive. It's an inductive approach that has an abductive framework for inference on the interface almost, right? Like it looks like abduction on the interface, but it's really, you need this large data set to train. And so no, I mean, we just don't know how to do that. And if we did any real progress on, like you said correctly, Pearl. So abduction and causal reasoning are very, very connected. And you can see why. Let me just say really briefly, when I said, if it's raining, the streets are wet, then you have the abductive version, which is I observe that the streets are wet, and then I go ahead and hypothesize that maybe it's raining. But so what you're doing when you're doing that is what Pearl is asking for as well. You're not asking for a correlation. You're asking for a causal connection that explains your observation. So it's really like you're looking at the effect, and then you're positing a set of plausible causes that are actually operative in that context, in that environment, in the real world. And so that causal piece is what Judah Pearl does such a good job of explaining. It can't be it's not an associationism, right? Like in his pyramid. Well, it just can't be, right? And so he goes into great depth. Effectively, that's restating the abduction case. I basically just used other language.
I agree.
We're making the same point. Yeah.
It's the same thing.
I don't know that. Go ahead. Yeah.
It's the same thing as saying that according to his pyramid, we are still at the first round. Yeah. We still need to go to the second and third, the order of possibilities. Very good.
Yeah.
Another question here, and this is in the direction of this one that we just discussed. This is from my student, Antonio. Thank you for the amazing talk. Really inspired since the publication of your book. To the best of your knowledge, is no group working over abduction. This is what we discussed. But do you have any guesses on how to try to tackle this? I guess no, because otherwise you would have like a brilliant startup.
Yeah. No,
and pocketing.
I don't, there's a, the only thing, what I see is interesting confluence or combinations of the knowledge graph community with the machine learning community. And so we might get some interesting recommendation engines, you know, that are explainable in the sense that because they're not using a black box inference, but they're actually also making reference to concepts that are structured, right? We might be able to use that kind of stuff to generate some more interesting applications, kind of like a next gen after just deep learning. But in terms of like this real like pie in the sky stuff, like we're talking, like, you know, abduction proper, you know, I just really, I don't have a clue. I mean, it's like the before Einstein asking how physics needs to change before special relativity. You know, I don't know. I mean, it's just like, yeah, it's frustrating in that sense. But I see us maybe in the next decade making some really interesting applications using the tools that we have, because I think we've been kind of stuck in this deep learning, kind of almost obsessed with, right, like the power of these networks, right? It's like at some point you've got to realize that, you know, there are other tools that solve problems better, and we need to start thinking as engineers and combining some of these tools, and that might really bring some interesting stuff, but it's not going to bring general intelligence, you know, from abduction, for all the reasons I said, because those two inference types don't. It's like saying if I know Spanish and French, then I can learn Russian, right? Like in terms of getting two inference types and getting the third. No, I mean, it's cool to learn Spanish and French, and hybrid systems might make you millions, like you said, you know, but that doesn't mean you know Russian, and it doesn't work that way. And it's the same with inference. So yeah.
So some could argue on the contrary. Just this week, probably you have seen DeepMind, I guess, launched Gato, which in Portuguese is like cat, and it's a giant network that, if I'm not mistaken, works with like 100 tasks, something like that. And one of the headlines that I was seeing is something like, Gato leads us a lot of steps closer to general intelligence. So, and when you see, it's a GATO, it's the new giant transformer that DeepMind launched.
Yeah,
GATO.
Okay.
It's cat sure. In English, and this word is in Portuguese is cat. So. Right.
Yeah.
So Gato is pretty much the same as GPT, but GPT is like specialized in language, and Gato is like specialized in more than 100 tasks. So some people could argue if you, okay, I have this GPT thing and it can generate text and it generates good text. How would you argue with this person that's pretty far from intelligence, and probably that text is just like combination of like these tons of data it was used to train with?
Yeah, I mean, so like those, I use those models at work in work, BERT and so on, and those models are extremely useful when, you know, 20 years ago we didn't have access to those pre-trained models, and so it was just a nightmare trying to figure out how we get word similarity, and you know, and NL generation was just a really hard problem, and you know, natural language generation. So I mean, those models are incredibly useful, but you have to understand, at the end of the day, you're basically projecting into a very large dimension vector space, and using something like cosine similarity, you're basically saying these words are all close in that vector space to these other words, right? And so there's no actual ground truth or understanding in that model, and even more damning, it's limited by that vector space is just a function of Wikipedia pages that you fed into it, right? So what that's the world, that's the universe, that's the whole problem, that's the white swan problem. You haven't seen a black swan. So in terms of actually getting a real flexible, you say you wanted to bridge from, you were mentioning generation, right? Like generating text, right? Say you wanted to bridge into an actual understanding conversational bot, you're going to need something else, because if they're, it's, and again, it's just because if it's not in that vector space, I mean, a conversation is potentially infinite, right? And so how many web pages equals, an infinitely malleable, a dynamic problem? We're just going to need something else, right? And so just yet one more way of saying this, which I think I've said before, but it's like saying, I've seen a million conversations, and so I can have this one. Well, that's not going to work, right? Like conversations don't work that way. You don't just say, look, bring me all these canned conversations. This one is most statistically similar. I'm talking to my neighbor, or I'm out on a date and I'm talking to my, potential, and I'm thinking, okay, I'm going to match what she's saying with this fragment that, that was in my data set. Well, it's never going to match, because there's something unique that's happening right there that you're not going to get. So those models are very useful, but they don't solve these bigger problems. They just don't. So, yeah.
I have one, I think that the excerpt of the book that brought me into reading the whole book of yours was like in page 5, when you say that we are paying the price for a myth, right? Everybody's believing that we are heading towards this AGI, and the price is too high. So as we don't have scientific reason to believe that the myth is true, and every reason to reject it for the purpose of our own future flourishing, we need to radically rethink the discussion about AI. So what would be your suggestions, like, to rethink these foundations? Like you said that one important thing to do would be think of possible ways of doing abduction. But in your opinion, is abduction the only thing that's missing? What else could be missing if we want to go like for AGI?
Oh, I mean, so are we talking about are we talking about how the myth is hurting us, or we're talking about what's missing in AI besides the abductive?
What's missing besides like the lack of abduction inference?
I don't have a super good answer to that, but I can tell you, and you probably know this as well, being in the field has a way of, we have all these brilliant people in the field, but they have a way of completely forgetting what the best work was 5 years ago or 10 years ago.
Exactly.
Right?
Exactly.
We're sort of always reinventing the wheel in AI. And there's so much, one thing we could do in the field is not get taken up by these hype cycles and connect our research so that, things that are, there are probably research papers that are extremely 22 that nobody's ever going to read because they're 2009, it was, right. I mean, it's just, and so the field itself kind of is in this collective amnesia state all the time. And just whatever the new shiny thing, everybody just starts running towards that. And I think, so that's just kind of a, maybe that sounds like a grumpy point about, but I wish AI was, I don't think physicists do that so much, right? Like they still remember, the previous
the basics and
so on, but the basics, they build on top of, like, AI people have a hard time building on top. So I think we're not making as much progress for that reason.
You're right.
Yeah.
The other day I was discussing this with some students, and I was giving a talk, and when I told them that in Aristotle, in the book of Politics, he already was discussing something about like an artificial being. And the students, well, no, artificial intelligence just came out in the 50s. So they don't even know history in those cases.
Yeah.
I have here a comment from Jones. Hey, Jones, welcome. Excellent reference for Alan Turing in his Mind paper, 1950. Brilliant talk, Eric.
In your book, you did talk about Gödel and others, but what do you think about the machines that Leibniz built? Do you know them? Some of them seem to be on the abductive side.
Who builds?
Leibniz, the mathematician.
Oh, I don't know. Yeah, sorry. Am I not getting it? Is LAT?
No, it's in the chat. It's Leibniz. Probably in English you spell it different.
Leibniz.
Yep.
Are you talking about?
Yeah, Leibniz.
The Enlightenment figure. Okay, yeah, sure. So I actually I'm not familiar with the specifics of his. He had I remember he had the idea that you could come up with a mathematical language that would prove false or true any statement formulatable in it, which Gödel actually did prove was impossible 300 years later, right? So that's the whole incompleteness problem. But also he actually, I think you're referring to Leibniz built a physical computing device, or is that what you're referring to?
I'm not sure. John, would you like to elaborate on your question? You can open your mic.
Yeah. Yeah, I'm not an expert on Leibniz, but I think that's what you're getting at, whoever asked the question.
Yeah, Leibniz did 3 machines. Two of them is a engineer's one, but one of them is abstract. This is my question. If you know if that machine is in the way of your thoughts in your book.
Yeah, I didn't. So I just mentioned. So I'm aware. So Leibniz worked on this thing, this problem that was a little bit like alchemy. It's sort of like when Isaac Newton was really obsessed with how to transmute lead into gold, and he also rewrote all the physical laws of the solar system, but he was just obsessed with alchemy. So Leibniz was obsessed with making a language that would be perfectly clear, so that there was no way that every statement could be, through a chain of really calculation or computation, would be found to be true or false. But that's actually not possible. So I didn't talk about this in the book, so I'm not like an expert on Leibniz, but I'm just trying my best here. But what Kurt Gödel said in the 1930s is, if you can include basically the successor function, so you have a +1, which is this is basically the piano axioms into a formal system, then you've got enough to create a contradiction in that system. So you actually can't do what the Leibniz's perfect language of truth. It's actually not possible to do that. Once you formalize a language, there will always be statements that are true but not provable that you can formulate. That's actually the incompleteness result. So I think Leibniz wasn't aware of that, but I don't know. I mean, he was a smart guy. Saying he was a smart guy was an understatement. He co-invented the calculus with Isaac Newton. He just dreamed up he was quite the genius. So sorry, I'm not an expert on Leibniz, but yeah.
Yeah, thank you. I have a question here from Marcos, and it's a difficult one. Thank you for the great talk. I would like to ask if you think that abduction and causal relations explain most of the ways, or all the ways, that human understanding and knowledge acquisition. So that goes also in the direction of a question of mine. We don't really teach children to acquire this abduction model. It just happens, right? So it's I have like a 1-year-old nephew now, and it's absurd the speed with which he acquires knowledge, and I'm sure that some of the abduction he already knows, and nobody taught him to acquire that. So what do you think? Are these like inherent of humans? How we acquire these? Is there a way to teach a machine to do that?
Yeah, I mean, it's a really key question, and I don't know. so if you go and you look at somebody like Chomsky, he'll say that there's just no way you can acquire that from empirical, from experience. So there must be deep structure. And, I mean, like something like that strikes me as true. And it's troubling for computer science because we don't even know if those are computational. We don't know what that, what those deeper structures are. We're in the realm of biology, and everything is, so this is I think a confusion about computation. Everything is computable ex post facto. Well, almost everything, right? So you can always simulate something after the fact, but the question is can you reproduce it, at time t? Can you do it at time to make it happen at t+1? And it's not clear that all of the stuff that people are doing, that we're doing when we're learning, like you said, language acquisition and so on, is really hard to figure out what that program would be. But look, I mean, this is getting into the speculative realm, right? But I wouldn't be at all surprised if 100 years from now, somebody had some sort of almost a Gödelian, almost impossibility proof that you can generate some of this stuff with pure computation. But I'm not going to go out on that ledge, because then people will start saying, oh, so you really don't believe? Look, I really just don't know. I really don't know. But it's puzzling how our own minds work. And the more you kind of think in terms of this inference, the more it's just really, it's like we have an effective infinite set of possibilities, and we always seem to be able to select the right one. And we're not iterating through the set, obviously, or we wouldn't be able to move in real time, right? So there's something very strange going on. We seem to be connected to nature in a very intrinsic way. It's very strange.
That's enticing.
Yeah,
for me, I used to say to my students that in machine learning, for instance, it's not magic learning. But when I think about the brain, what happens in the brain, it really seems to be magical how we can acquire knowledge. And if a person gets hurt and half of his brain is chopped off, and the brain, like, he wires itself so that he gains some of your abilities. That's amazing. Another thing that I was thinking is in line with what you are discussing here, and given like this extraordinary power of the brain, do you think this is like a speculation? Do you think that we would be better off trying to understand the brain and replicate it artificially somehow? And we have like lots of AI people doing that. Or on the other side, we try to do something completely different and don't worry about like emulating the brain. So which side would you think is more promising? It's a speculation, of course.
Well, I'm an engineer and I'm not a neuroscientist, so you can guess what I'm going to say. I suspect that so first of all, you have to point out that the blue brain was an early attempt to simulate a rat's cortical, complex. And his name was Henry Markram, he's the former head of the Human Brain Project overseas. And so, but this has been going on, and billions of euro have flowed to this kind of work. And basically, so far all these projects have been a failure. And one of the main reasons is just that if you have a low level set of neurons, right, and then you do something called predictive neuroscience, where you say, look, we know 8 out of 10 of these connections, then we're just going to predict the other 2. But if you have a failure rate of 2 out of 10, it's very unlikely that you're going to converge in 100. You're not going to get a brain, you're going to get something else, right? And so there's just a complexity problem at the level of the simulation of the neurons and their interactions. And then you have the MESA circuits, right? Like, so that how they fit together. And it's at any given point, it's like putting Legos together, but at any given point, we don't have the explanations that we need for, say, intelligence or common sense reasoning or something. They fall out of that picture way before we get to a kind of, like, say we want a cognitive architecture, right? So, you know, somebody like Ben Gertz will, you know, say, okay, I've got this cognitive architecture, and, you know, I look at it sort of cynically and I just see like circles and lines drawn. It's like, you know, okay, like it's a schemata. It's like, it's not clear that that's, but, you know, but my point is though, I'm trying to make this point. It's a little bit difficult point to make here, but I'm saying if you start from the ground up as a computational neuroscientist, you don't end up with a cognitive architecture. You sort of, you fizzle out in complexity before you ever figure out how these things fit together. So that might be a weakness in that approach. You just can't, it's too complicated to do a ground up simulation. You're not going to get the conceptual structures that you need from that low level analysis. And so I suspect that's true. And I suspect that's why those projects keep sucking up a bunch of money and then failing because they're just, yeah. And so I think the best thing we can do as engineers is solve interesting problems. And, you know, I'm a computer scientist, but I think of myself as basically like I'm building a bridge and I have a set of tools available to me. And so, you know, I feel like we should take on hard problems. I think we should be problem driven rather than, you know, method driven. Like we're going to do the brain thing and then it's like, okay, look, I think we should, as a field, we should take on hard problems. And then as we solve those problems, we'll gain insights into, the hope would be that we gain insights into what an AI really would look like. But that, you know, that's kind of my prejudice about that. Yeah, but yeah.
Okay, thanks a lot. One last question. After all the lit studies that you did and the book that you wrote, and based also on your experience, and you mentioned here that many people, they don't read like the classics. They just look at the last 2 or 3 years papers. Would you recommend some 2 or 3 really important books that marked you and that you think like are very important for students to get their hands on and read and learn new things?
So just any books on AI, even old classic ones, just
it does not need to be in AI. Books that you read
I
that
see.
Allow you to be critic about the way that you are of course, C.S. Peirce's work is like awesome, and I was interested in C.S. Peirce before, and after I read your work, I looked at some of his works, but I don't know if it's an easy reading for many people, but
No.
other kinds of readings that you've done in the past that you think would be interesting for the students to read as well.
Yeah, so I have a couple of examples, but they're mostly in AI. There's one neuroscience book that I would point out, but the Feigenbaum, I'm sure you know, Edward Feigenbaum. He wrote a book called I don't remember what it's called actually, but it was published in 1976, and he sort of anticipates a lot of the problems that we're going to have with software in general, and also with AI in specifically. And it's a fascinating read. He was of course a famous computer scientist, and I'm sorry, I think I'm screwing up his name. It was Weizenbaum, not Feigenbaum. I'll have to get the reference. Anyway, it's a classic text written by an AI guy in the late 70s, and it's very strange reading it today because he really anticipates a lot of the problems. One of the problems that he points out, I really need to get his, people will find it's, yeah, maybe I can, before this is over, maybe I'll type it into the chat. But one of the problems that he points out is that at some point when our software systems get large enough, we're going to stop understanding exactly how they work. And this is coming from a technical guy, right? Like, he's not saying this is a futurist, but and he's saying like this is going to be a major problem for people making sense of the world. We're filling the world up full of software. And it's kind of funny, you know, hearing that in 1976 and then realizing that this is a kind of a big problem that we have. So I read that book to write The Myth, and it still repays a great reading. Yeah. More to the present day. There's a book called Atlas of AI that came out basically the same year as my book came out in 2021 by Kate Crawford, who's a computer scientist at Yale. And she talks a lot about the real costs of using these. She talks a lot actually about the GPT-3 and the BERT models and how expensive they are to train. And so, you know, one thing I'd like the students to focus on, and you can go, you don't have to go crazy with this. Sometimes when I'm in a bad mood, I call it monster truck AI, like just to like the, you know, those giant truck. Well, the like, you know, they're very compute intensive. And so one thing, that's fine. I mean, look, you know, the powerful AI takes a lot of electricity, but wouldn't it be great if we had, the brain doesn't take, you know, anything like that at all, right? To be, you know, infinitely, or not, you know, not infinitely, but so much smarter. So wouldn't it be nice if we thought about low energy ways to develop intelligent behaviors, right? So we don't need to train 75,000 parameters, you know, with a cluster of special purpose GPUs, you know, where the lights in mid-sized cities flicker when you're training them because there's so much power coming out. Like, okay, fine, but you know, so that book, Atlas of AI, she really does a great job of explaining the costs involved in our obsession with AI technology. But you know, she's also a computer scientist, and she's not suggesting that we stop doing AI, but I think if you have a critical eye, it's maybe easier to see other paths forward, right? So
exactly.
So that book is that's a great book, Atlas of AI. Yeah, I can't think, the reading list. Well, of course, Judea Pearl. Well, now I'm giving you AI books, but Judea Pearl's book is very good.
Yes.
His book called
really good. Yep.
Yeah,
I like
he's
it
yeah, I think he won the Turing Award or something. He's a brilliant guy down at UCLA.
It's not for nothing that he won the Turing Award, right?
Yeah. So if you want to read just a really fantastic book about why causality matters in AI, you know, of course, pick up the Book of Why. You know, there's another book by Marcus, you know, Gary Marcus. He wrote
Rebooting AI.
Yeah, Rebooting AI is a good read. It's skeptical. It's kind of in the same vein as mine, right? So, but he has a slightly different way of, you know, exposing those ideas. So I think Rebooting AI is also good. And then I would say, you know, I guess I would even say Stuart Russell's book. I actually disagreed with almost everything Stuart Russell said
but it gives you another way of thinking.
Yeah. I mean, like, that's the other thing. Read stuff that you don't agree with. Like
exactly. I read that book as well.
Yeah. I thought, okay, this is what's wrong with the world. But you know, and nothing against, you know, he's a brilliant, also, you know, he's co-author of the textbook that everybody bought.
AI book. Yeah, exactly.
Yeah, he knows what he's talking about, but it's just his view on, you know, we need to have the AIs watching us to figure out what we want and what we don't want. It's like, I don't want an AI watching me to figure out what I'm doing all the time. And it's just very strange. But yeah, Stuart Russell's book, it's called, I can't remember what it's called, but it's worth reading for a very different take on AI than mine, certainly. Yeah. But yeah, I mean, I guess that the other thing I would just, if I'm called upon just to pontificate and give advice here about books, I'll read a book about the economy just to kind of flush my brain out, right? So I'll just read something completely different so that I kind of can get, you know, sort of more, when I come back to AI stuff, I'm sort of more focused. So I'll do that as well. I'll pluck out you know, some random, I think I read Thomas Piketty's Capital. Or I tried. I tried anyway.
This one?
Yeah, right. I got him.
I am reading it right now.
Thought,
it's really good.
Yeah. So it has nothing to do with AI, but it's kind of, you know, I'll do that deliberately, just as a writer, just, you know, yeah. But yeah, that's a rough read, but that's funny that you had it right there. Yeah.
Yep.
My
I'm
copy
reading it.
is just out of reach. My copy is just out of reach too. So yeah.
Very good. That's a coincidence. All right,
Yeah.
Erik, thank you very much. I don't have any other questions here. It was awesome to have you and to discuss these topics. I'm sure that everybody here liked it. I hand over to Marcos to also thank you. Marcos?
Yeah.
I would also like to thank you very much for this great talk, and it's very nice also that you have talked without any slides, so just from your memory and your experience. It was very nice. Thank you very much.
Well,
Thanks a
thank
lot.
you. It was wonderful. It's wonderful, and I'll see you guys down in Brazil sometime. How's that?
Yeah, sure.
Yeah, it would be good.
Yeah,
Thanks a lot.
you bet.
For
Get out of the
everybody
state, get out of
here.
Go ahead.
For everybody here, also thank you for joining us. Remind you that next week we have another talk. This one is going to be by Michael Brownstein, the chief engineer of AI in Twitter. So stay tuned. And Erik, once more, thank you very much for your kindness and for the discussion.
Thank you very much.
Goodbye.
Thank
Bye-bye.
you very much. Have a wonderful
Bye-bye.
evening,
Thank you.
everyone. Thank you.
You too.
Yeah.